Welcome to online seminar on design, operation and maintenance of commercial reverse osmosis and membrane filtration systems. During this seminar, we'll cover all the subjects related to membrane systems design and operation, starting with sources of supply of raw water, then following with processes of feedwater pretreatment. Then we will discuss the configuration of membrane unit, and finally processes applied to stabilize product water. We'll also discuss relevant aspects of modern approach to membrane system design and optimization of process economics. My name is Mark Wolf. I have compiled the seminar material and will conduct this presentation. Welcome to
The seminar material is divided into number of modules. In the first module of the seminar, which we are starting today, we'll discuss subject of membrane structure, membrane manufacturing, configuration and performance of aeromembranes and membrane modules. We'll follow up with information on terms and relations that I apply in the process of design, operation, and evaluation of performance of membrane modules and membrane plants. We'll also discuss process parameters and their effect on performance and longevity of membrane elements and stability of operation of membrane systems. In the last section of this module, we'll discuss selected subjects of water chemistry as they are applied in operation of membrane plants. This will include water chemistry of the pretreatment processes of treating raw water to produce feed water of required quality. We'll also discuss the processes of treating aeropermeate to stabilize its chemistry, to comply with health regulation, and also to prevent corrosion of materials of construction of distribution networks by low salinity product water. We'll end up discussing configuration of commercial membrane plants of various capacity. Through the presentation, a dual system of units will be used, both metric and US unit system. The conversion factors between more frequently used units in these two systems are listed in the slide shown on the screen. Some of more important procedures used in the design, operation, and performance evaluation of the membrane systems have been compiled and published by professional organizations. One of the more complete sources of such publication is American Society for Testing Materials, in short ASTM. List of selected ASTM procedures are included on this slide. The list also includes some useful publications that contain relevant information on membrane technology, processes, and applications. When considering desalination as an alternative source of new water supply, one has to evaluate its economics in the context of other water supply alternatives, which are listed on this slide. Good indicator of economic feasibility of various alternatives of water supply is their energy requirement. Energy is usually the major component of operating water cost. Majority of potable water is supplied from natural sources, which are surface water and low salinity underground aquifers. If natural sources of potable water are located close to the demand center, the energy associated with supplying of potable water is quite low, usually below 0.1 kWh per cubic meter or 0.4 kWh per 1,000 gallons. However, if water has to be pumped over long distances or to a significant elevation, the energy requirements can increase significantly. In some cases, the energy usage could be significantly higher than 1 kWh per cubic meter or 3.8 kWh per 1,000 gallons. Usually, supply of potable water from natural sources is the lowest cost water supply alternative. However, the water quantity available from natural sources is limited. The distribution is not equal between different locations and also could fluctuate seasonally. At locations where supply of potable water is limited, one has to look to other alternatives. One of the alternatives that have potential to augment existing water supply is desalination of brackish water. In the brackish water desalination process, energy is required to pump water from the underground aquifer to the plant site, drive the membrane separation process to force water through the membrane, and power the auxiliary equipment of the plant. As shown on this slide, the total energy requirements of brackish desalination processes is usually higher than the low range of energy need to supply water from the natural sources. However, if in the first alternative the water has to be pumped over long distances or to high elevations, brackish water desalination could produce water at lower energy usage. Among the desalination solution of supplying new water, the brackish technology could provide water at the lowest cost. The limitation of producing water through brackish water desalination is limited to availability of brackish water sources. Another serious limitation are constraints related to disposal of the concentrate. In the brackish water desalination process, 15 to 35% of the brackish water processed by RO unit has to be disposed as a concentrate of salinity much higher than the salinity of the original feed. Especially for the inland locations, disposal of concentrate from brackish plant could add significant cost to the desalination project or even make the desalination project not feasible. Another alternative of producing new water is desalination of seawater. Seawater is available in unlimited quantity. However, for practical reasons, the seawater desalination plants have to be located at coastal sites. Otherwise, supply of seawater to the plant and returning of concentrate back to the ocean would be prohibitively expensive. Seawater has much higher salinity than brackish water, 3% to 4 points of dissolved solids, compared to 0.1 to 0.5% of concentration for majority of brackish water. Due to higher salinity, the osmotic pressure of seawater is higher than osmotic pressure of the brackish water. Therefore, as we will learn later, the feed pressure has to be higher and the energy requirements will be higher as well in the seawater application compared to the brackish water as shown on this slide. In addition to the limitation of location close to the seashore, the seawater desalination faced serious environmental concerns of the effect of operation of the desalination system on the marine life. The concerns are related to removal of marine organisms with seawater feed and potential environmental impact of disposing of high salinity concentrate back to the ocean. The desalination community is working very hard to develop engineering solutions that would minimize environmental impact on marine life from operation of RO desalination systems, and some effective processes have been developed already. The last membrane process listed on this slide is reclamation of municipal effluent using integrated membrane technologies. Due to low salinity of municipal effluent, the energy requirement of this process is similar to the process energy required for desalination of brackish water. The municipal effluents are available in vicinity of majority of population centers. The membrane technology for wastewater reclamation is very reliable and well developed. However, problem of public perception limits use of product water from this operation to irrigation, industrial use, and limited aquifer injection. Aquifer injection is applied mainly at coastal locations to prevent seawater intrusion. There are two basic categories of desalination processes: evaporation and reverse osmosis. The evaporation processes include multi-stage flash (MSF), multi-effect distillation (MED), and vapor compression (VC). Both MSF and MED required low energy steam to increase temperature of seawater, then to produce water vapors, which are later on condensate into very low salinity product water. In addition to low energy steam, both MSF and MED require some quantity of electric energy, shown on the energy graph as blue bars, to pump seawater to the plant and also for internal recirculation. In the vapor compression process, electric energy is used to drive the compressor to pressurize water vapors to increase their energy. The energy requirement of the distillation process is only slightly dependent on feedwater salinity. For this reason, evaporation processes are used mainly to desalt seawater onto concentrate high salinity brines. The reverse osmosis utilizes only electric energy for the desalination process and to power the auxiliary equipment. The electric energy drives electric motors of the high pressure pump, which increases feed pressure to the level required to drive the feed water through the membranes and produce aeropermeate. The energy requirements of reverse osmosis process is function of salinity and increases with feed water salinity. However, even in seawater application, the energy requirement of reverse osmosis process is significantly lower than the energy requirement of distillation process treating seawater. The energy requirement of reverse osmosis application in treating brackish water and low salinity wastewater is significantly lower than in treatment of seawater. The distillation desalination processes were the first applied commercially and have good record of high reliability in seawater application. Presently, about 50% of seawater desalination systems are still utilize distillation technology. However, the number of new desalination systems that are being built are in favor of membrane technology, mainly to lower energy use of membrane processes.